So over to you, Griet, and please do tell us about the CarbOcean project. Thank you.
Thank you, Adrian. Hopefully you see my screen right now.
I can see it, but it's not in presentation mode yet.
Yes. How about now?
Yep.
Okay.
Perfect.
Yes, thank you. So yeah, I'm Griet. I'm based in Ghent University, where I am establishing a research team on remote sensing and autonomous observations for marine ecosystems and carbon cycle research. And today, I had the opportunity to introduce the CarbOcean project, which is a 5-year project starting grant funded by the ERC, the European Research Council, and it kicked off almost exactly a year ago. So it's an introduction to the project today. So it's about the biological carbon pump, and of course you are all specialists in the area, so I will not dwell too long on this. So basically, it's the synthesis of biogenic carbon, mostly in the form of particles in the euphotic zone, and then subsequent transfer of these particles to the underlying twilight zone and further on to the deep ocean and the seafloor. And this biological carbon pump leads to the sequestration or the lowering of atmospheric carbon dioxide levels by 40%, as obtained from a modeling study in which the pump was switched on and off in a pre-industrial steady state ocean atmosphere. And so, okay, these biogenic carbon particles, they exist either in the form of organic carbon or inorganic carbon, as you can see, according to the original definition of Volk and Hoffert. So as we all know, this pump is rather under constraint, where I have added here the range of estimates of export fluxes from the euphotic zone and the ones how much of that flux survives the transit through the twilight zone and reaches 1,000 meters. It's a reduction by an estimated 90% of that flux. So as you can see from the estimates of export, there are large uncertainties, and the range is almost as high as our annual anthropogenic emissions. What is particularly poorly understood are the processes that lead to the losses in the twilight zone, where most of this carbon is remineralized and transformed back into CO2, and the depth at which that happens determines the sequestration time of carbon in the ocean, ranging between decades in the upper twilight zone to nearly 100 years towards the bottom. But of course, yeah, these times scales, they also depend on the local ocean circulation. So there are quite a bit of limitations when it comes to the conventional approaches, which trap sinking particles. They require ship support and typically limited coverage. And temporal frequency, of course, this is embarrassing to say after the excellent talk we just heard about the time series of particle traps. But okay, in generally speaking, there is a lack of observations. Another thing is that a whole lot of work is done towards the organic carbon component of this pump, but a lot less effort is focused on the calcium carbonate component of this pump. So what we will do in CarbOcean is develop a robotic approach to study both of the components of this pump by developing new technology that is capable of observing or partitioning carbon into its organic and inorganic components. So as you can see, the organic carbon pump is driven by photosynthesis, and the carbonate counter pump is driven by calcification. And the differentiation between organic and inorganic carbon is important because, as you can see, the organic carbon pump results in a lowering of the partial pressure of CO2 in the surface ocean, whereas the carbonate counter pump has actually the opposite effect due to the calcification reaction, which consumes two bicarbonate ions and then shifts the carbonate chemistry equilibrium towards a higher PCO2. So yeah, so the net drawdown of CO2 by the biological carbon pump is determined by the balance between these two pumps. So what we want to investigate in CarbOcean is a quantification of how much of this PCO2 drawdown is countered by the carbonate pump, which is determined, as I said before, by the ratio of organic to inorganic carbon in sinking particles. And the other hypothesis that we want to test is to see whether calcium carbonate, which has a density that is about 3 times higher than the density of organic carbon, whether these calcium carbonates, this high density material, acts as a ballast for organic carbon particles and makes them sink faster, and thus enhancing the transfer efficiency of the organic carbon pump. So so we are now in the first year of the project, which is very much about the technological development. So we are working on the development of an optical sensor for the detection of calcium carbonate, which is based on the principle that this biomineral is strongly birefringent and changes the polarization state of scattered light. And as you can see from this figure by G.M. Bishop, in the ocean, the particles that naturally occur there that are strongly birefringent are calcite and aragonite. So it's a cross-polarized transmissometer, which is similar to the concept of the transmissometer developed by Jim Bishop's team, but it's different in the sense that we use another type of polarization, and we also changed some essential elements of the transmissometer. So in terms of technology readiness level, we are in this phase of having established an experimental proof of concept using different types of cultured coccolithophores, which have a strong diversity in terms of size and shape. And we are working towards an experimental prototype with the industrial partner by October of this year. And then the next development steps are the validation of this prototype in situ first from this ship's CTD rosettes, and then integration of this sensor onto a robotic profiler of type biogeochemical Argo. And then, so once you can see here also that there is a second transmissometer that is an unpolarized version, which if you measure both of these things, you can work out how much organic carbon is contained in the particles. So what we get is the concentration of organic and inorganic carbon particles. The nice thing about transmissometers is that they act as optical sediment traps as the particles accumulate on the upward-facing windows of the transmissometer when the float is parked at its parking depth, typically 1,000 meters. but the most recent floats, they also stop at just below the euphotic zone, for example, where the export fluxes can be quantified. So the idea is to, other variables will be measured from this float, which are some of you may know the biogeochemical Argo core variables. Many of these are included here. So it's temperature, salinity, depth, pH, dissolved oxygen, chlorophyll A, particulate backscatter, irradiance, and if I can secure additional funding, I would also like to include a particle camera, UVP6. So the idea is to deploy 6 profilers in 3 ocean provinces, where in each province we would deploy 2, and the anticipated date for that deployment would be 2024. So a little word about, about biogeochemical Argo. I'm not sure how many of you are familiar with this, but it's a recent extension of Argo profilers with biogeochemical sensors, and these really greatly increase the sampling frequency and the resolution of some of the key variables of the biological carbon pump. As shown here is a status map of last month. So we have about 500 active profilers to date, and the target size is to have thousands of them operational by 2025. And what we can get from those profilers are phytoplankton biomass, size indicators, and net primary production, the sinking particles as well as their sinking speeds, and carbon fluxes from the optical sediment trap. So in the publication of the science and implementation plan of BGC Argo in 2016, 6 core variables were chosen based on their relevance and at that time the maturity of the technology. But this is fast changing. So the latest development that is really exciting is a zooplankton, a particle camera that is capable of counting and enumerating and identifying zooplankton types and aggregates. And so what CarbOcean will do is add a capability to biogeochemical Argo floats that separates total carbon into organic and inorganic fractions. So to summarize, the objectives of the CarbOcean projects are to develop and deploy a pilot array of 6 profilers of the next generation biogeochemical Argo floats that are capable of observing the 2 components of the biological carbon pump. To better understand the role of particularly the carbonate pump in this overall biological carbon pump, by quantifying the counter effect, and by examining the calcium carbonate ballast effect. What we would also like to do is bridge these observations to the biogeochemical modeling community for a better representation of the ballast effect, which is already included in many models, but is based on limited observations. And what we also aim to achieve is to establish an observational baseline for the impact of ocean acidification on calcifying plankton. So CarbOcean is very much a team effort, where most of us are based in Ghent University, in my team, but also in the liquid crystals and photonics group. And also I'm collaborating with people from the Phytoplankton Culture Lab and with support of Flanders Marine Robotics Center, and also external collaborators with different expertise in optics, Georges Fournier, and in biogeochemistry, Hervé Claustre, Jean-Pierre Gattuso, and Leonard Bach in Tasmania. And I think with this slide, I will close. So if you have any questions or...
Thank you very much. Excellent talk. Some very impressive technology there. Let me look at the chat. We have a couple of things there. Let me go to the first one. So first off, Lauren, do you want to ask a question?
Sure, yeah. This is a great talk. Thank you so much. It's really exciting stuff. I'm a PhD student at Rutgers University in New Jersey, and really happy to be on this call. I'm sorry if you already mentioned this. I may have missed it, but did you mention what the size class range the transmissometers target, if applicable? I'm not really sure how it works, but I was just curious if there was like a specific size class range it targets.
Yeah, it's a very good question. I did not mention it. So transmissometers are in the micro phytoplankton size range. So with spikes, you can detect large aggregates, but typically it's sensitive to the smaller particles. So what we can get with this polarized transmissometers is mostly coccolithophore calcite. That's why it would be very interesting to add a UVP or an underwater vision profiler instrument to those floats to be able to quantify theropods and forams.
Excellent stuff. Thank you so much.
You're welcome.
Yeah, interesting. So I saw there was another comment there as well. Yibin, would you like to answer your question?
Sure. Yeah, very interesting project. I have a question. I'm wondering how you calculate the PIC and POC export flux from the flow observed PIC, POC inventory or concentration, because as far as I know, it requires actual information such as the sinking rate to do this. And also, if we want to quantify the sinking rate from the BGC flow, it also requires a much higher temporal resolution, which usually higher than the typical resolution of BGC flow, such as 10 days.
Yes, that's a very good point. It's indeed true that if we want to use Nathan Brick's methodology to estimate the sinking speed of large particles, then we need to have a very high temporal resolution and vertical resolution. But this is something that can be achieved with this type of float. So I will adopt the 1 meter and less vertical resolution and the sub-weekly temporal frequency. That's one part of the question. And then the other part is, how do we get organic carbon fluxes from the float, if I remember correctly. So it's basically the optical sediment trap technique that was developed by Jim Bishop and later on by Margaret Estapa. So it's a measure of the attenuants that you collect when the particles fall on the transmissometer window, and then you can convert that into carbon units. But you need to do the calibration, of course, and that's a very tedious job that that will require the concomitant deployment of the floats with sediment traps. So if we want to really get the carbon fluxes out in carbon units, yes, that's something that will need to be done.
Oh, okay. Thanks for explanation.
So can you turn that round? I mean, does that mean that you can, provided you do the calibration, you can also calculate the sinking speed because you have the flux and the concentrations?
If you have flux and yeah, I suppose you could. I suppose you can, but it's not like that this kind of technique is already existing.
Yeah, I'm just thinking, you know, from the point of view of a modeler who, you know, syncing speed data is goldust. You know, there are a number of ways that it can be estimated. I just wondered if this potentially gives us one extra way that we could do that, then that might be an extra sort of side benefit of your approach.
Yeah, I think it sounds like that could be. So if you have the time variability of the stocks and you measure the fluxes at different depths, well, at least like at the below the euphoric zone and at 1,000 meters, then it should be feasible, yes.
Thank you. So you can see Clarissa has a question. Clarissa, would you like to ask your question?
Yeah. Hi. So I really like the idea of looking for calcium carbonate with a visual technique. I was just wondering if the particles are actually homogeneous, or if you might have the organic carbon surrounding things like forams, for example, because forams like to hide sometimes in a particle. So have you made any observations or estimates for that?
We haven't tested it on forams yet. We're only using coccolithophores at the moment, but they also have an organic structure in it. Well, what happens is that the biomineral structure of calcium carbonate is the depolarization of the light beam is dependent on the thickness of the calcium carbonate. Also, yeah, and on the concentration of the material.
That's really good.
Yeah, that's how it works.
Thank you.
Thank you, Clarissa. Is there anybody else who would like to ask Griet any questions? I should keep an eye on what the time is, actually. I think we've got time for another question or two if people want to add anything in the chat, or just if they want to just ask a question now that the let me just scroll down, just make sure I haven't missed anything. Jamie, go for it.
Hi. So just following on from the comment you just made, if you could measure the thickness of the calcite in a foraminifera, that would be super useful, because then that kind of is then the pic-to-poc equivalent of, say, a coccolithophore. So we're kind of, our group in Bristol is working on that at the minute, and kind of tying up the pic-to-poc of a coccolith and using size normalized weight as a pic-to-poc proxy for a foram. So that would just be really neat if you could do that.
Yeah, but you have to know that the sensitivity of the optical measurement is to the whole pool of calcium carbonate in the water. So if you have forams intermixed with coccolithophores, what I'm imagining is that because the foraminifera are much thicker, that will cause spikes in the depolarization, and might give us a way to detect them.
Okay.
Pretty much like the spikes in backscattering or beam attenuation are correlated with the large particles.
Okay, thank you very much. I can't see any other questions in the chat, and we're approaching the hour. So I'd like to thank our two speakers, Mike and Griet, once again. If you have any questions, particularly if your connection has let you down, please, do email them. I'm sure they would be happy to answer any questions that you might have. And if you missed anything because you were thinking or answering the door at the time, then the talks will be on the web, hopefully, in the next couple of days if you want to catch up on any of them. So once again, thank you to the speakers. Thank you to all for joining the call, and we'll be advertising the June call in the next couple of weeks.